So we've been talking about work, and now we're going to talk about another very closely related topic, and that is energy. Energy are transformations that we see take place all over the time, all of the time, but it's difficult for us to see energy itself. We can see when something has a lot of energy, or like we said before, when something doesn't have enough energy. We can see different forms of energy, like light, or a waterfall, or a car moving down the road, and talk about the energy that these things contain. But we want to talk about transformations and how those come about, and then the work energy theorem as well. So there's a lot of different types of energy, and energy is constantly transforming from one type to another. Some of these we're very familiar with, and others we're not so familiar with. But what we want to talk about in our discussions will be kind of a closed system where all energy is conserved, where we're not losing energy at all. We're accounting for everything that we have. So remember that we talked about doing work and how work is a force being applied to an object and the distance that the object moves, and making sure that we have a component of that force in the same direction as the motion. To do work on an object, we're giving it energy. And then there's this other thing about, well, how quickly can we do work? And that's where we start talking about power. Power is the rate that energy is converted from one kind to another. It's the rate that we can get work done. We say power is work divided by time. Remember, work is measured in joules and time is measured in seconds. So the unit for power is a joule per second. And so when you start looking at, electricity creating light, and we talk about how many joules per second of light energy is emitted, we measured those in watts. A watt is the unit of power. 1 watt is 1 joule per second. So we can kind of compare how much work somebody does, or in this case, the work that two people do. If they lift the same force and the same distance, they're actually doing the same amount of work. But if they do it in different amounts of power, or different amounts of time, they're exerting different amounts of power. And then kind of if we take a close look at these two guys, we can understand why they're capable of doing this in different amounts of time. But there's a couple different units for power. Some are small units, like a watt is a relatively small amount of power. But other units that you might be familiar with have to do with motors that you've seen, and that's a unit called horsepower. And we have a conversion from horsepower to watts. It takes 746 watts to make 1 horsepower. But if you read this information, you kind of figure out about where the unit of horsepower came from. It's kind of a neat historical perspective. And we could talk about different machines. I'm not going to spend time about looking at this, but I do want to talk to you a little bit about kinetic energy. So I know you're familiar with kinetic energy being the energy of motion, but we want to talk about how that actually translates, right? So we understand if an object is moving, then we're concerned with how much mass it has and the velocity that it has. And so we talk about the kinetic energy that an object has being calculated as 1/2 mass times velocity squared. And so if you take 1 kilogram and you were to move it or 2 kilograms and move it at 1 meter per second, and we considered how much energy this had, that should be the equivalent of 1 joule of energy. Kinetic energy, like I said, energy of motion. And then this is the big part about this unit, the work energy theorem. Basically, when you do work on something, like we said earlier, you're giving it the energy that it has. You're changing the energy of that object. And we can't measure total amount of energy that something has, and so we're mostly going to be concerned with how much energy did it change by. To measure the total amount of energy something has, we would have to burn the object and then allow all of that heat to go into a known amount of water and measure the temperature change. And We know the specific heat of water, so we could determine exactly how much that had, but it kind of ruins the object after that, right? So we're not going to be looking at that. We're going to be looking at how much change there has been in the energy of the object. So we're looking at a change in kinetic energy being caused by work done. If you take a box and you lift it up a certain height and you're holding it above your head, well, you're doing work on it and it is gaining potential energy. And since it's up above the surface of the earth, it's gaining gravitational potential energy. Well, that stored up energy could then become kinetic energy if the box were to start falling. And so we understand that the kinetic energy that it gains is a result of the work that you did on it to get it to that height. So the change in kinetic energy is always the final kinetic energy minus the original kinetic energy. And that would be equal to the work done. Change in kinetic energy is measured in joules. Work is also measured in joules. So this is an easy transformation for us. Here's a couple practice problems that you can take a look at. And then opposite the kinetic energy, if something doesn't have kinetic energy, it would have potential energy. This combination of potential and kinetic energy is called mechanical energy. And I know that you know of many other forms of energy, chemical energy, nuclear energy, but gravitational potential energy is the energy that something has because it's been lifted up to a certain height above wherever you decide 0 meters is. So if we decide 0 meters is the floor and we take a ball and we lift it 1.5 meters high, then it has a certain amount of potential energy. If we were to shave off the wall of the classroom and look at this from outside, we would not agree that the ball is at the ground. But for our purposes, we're saying, hey, the ball is on the ground. You know, here's ground zero. I'm not assuming things are going to go through the floor, but it is important that I establish that height where I'm going to say at this point it has no energy, and so if I lift it higher above that, it has some energy. So gravitational potential energy, or any kind of potential energy, is stored energy. In this case, it's stored energy because it's stored in the gravitational field. So when you lift something up, gravity can do some work on it and pull it back down. The symbol for gravitational potential energy is a U with a subscript G. U is potential energy. So if it's UG, think up against gravity. It is calculated as mass times gravity times height. Remember that we also know mass times gravity is force. That's weight. So we could also say, well, it's the weight of the object times the height. Wait, but that's also force times distance. So this is kind of connecting work and energy. All comes back full circle again. And another practice problem. And then we want to talk a little bit too about the total energy. So the sum of kinetic energy plus potential energy in a system is the total mechanical energy. In a closed system, that total energy should always stay the same. In other words, we're just going to be constantly trading potential and kinetic back and forth. If you think about a child on a swing, when they're sitting at the bottom of the swing, that's the lowest that the swing can go, just wishing that somebody would give them a push, then we could say, okay, at that point they have no energy. But if you come behind them and you give them a really good push, like, the good push, like run underneath them, hold them up in the air, ask them if they're ready to go, and then you've raised that a certain height, now you're storing potential energy in that swing, and then if you step out of the way and they fall down and start moving faster and faster and faster, this potential energy becomes kinetic energy, and then the kinetic energy starts climbing and gaining potential and losing kinetic, and this process happens over and over again. And it would happen forever if we didn't lose energy to anything else. But we hear squeaking and friction, and there's some mechanical energy that's lost to heat and sound in this swinging child at the playground, and eventually all of that energy will go away, and it will actually all become thermal energy, heat and sound. But we're going to be measuring changes in kinetic and potential energy, and assuming that our system is a closed system, and in a closed system, energy is conserved. So the total amount of energy that you start with at the beginning and the total amount of energy that you start with at the end are always the same. If we were talking about a roller coaster at the top of a hill, we could say that the energy at the top of the hill is always equal to the energy, say, at the bottom of the hill. Well, at the top of the hill, you might have potential energy, gravitational potential energy, and kinetic energy. We don't know. But this will equal the potential energy at the bottom and the kinetic energy at the bottom. So if you were climbing to the top of a hill and then you went down to the bottom, this next hill that I got to, in real life, I can't get higher than this hill, than the first hill that I started at. Because all along the track, I'm losing energy to friction and sound, and so that's an open system. If this was a closed system and there was no friction, well, I could climb right back up to the very top that I came from before. But I can say that the energy at this point has to be equal to the energy at this point. The total, it's going to look different. I have more potential energy here and not very much potential energy at this point. I have very little kinetic energy at the top, but a lot of kinetic energy at the bottom. So these are just transformations that are taking place. And we'll study those a little bit more as we continue on. So the total energy is converted from one form to another form. And we can really say, we're going to say, hey, this is kinetic energy and potential energy, but there's also some internal energy that talks about like the heat energy that something has. You take a ball and you bounce it on the floor, you can hear it bounce. The floor begins to vibrate, so you're giving some energy to the floor. But if you put a very sensitive thermometer on the floor, you'd also see that it heats up, just like what happens when you clap your hands together. Your hands heat up too. So we're constantly converting kinetic to potential, and then maybe some stored energy that might be even elastic energy. Maybe the ball deforms a little bit, and then some heat as we go through these conversions. But so it's important for us to decide, is our system a closed system or is it an open system? And in a closed system, the laws of conservation of energy always apply.